Welcome back to the Deep Dive. Our mission today, well, it's about tackling something a lot of network engineers deal with, this kind of architectural border wall. You know, the point where the super specialized data center network, the DC, runs right into the huge wide area network, the WAN.
Yeah, that DC-WAN boundary. It's a classic headache.
Right. They've acted like these completely separate worlds speaking different protocol languages.
Absolutely. And that requires complex translation just for them to talk to each other.
Which sounds painful.
It is.
Huh.
That translation, it's the source of a lot of operational pain. When you look at the current setup, you're really seeing a multi-protocol environment.
Okay.
And our goal, the technical aim here, is to get seamless end-to-end connectivity. You want service delivery across both domains, the DC and the WAN, without all that protocol friction.
Right. Smooth sailing.
Exactly. And the source material we're looking at today argues pretty strongly that there's one solution ready to basically eliminate this whole problem set.
And that is?
Segment routing over IPv6, SRv6.
SRv6. Okay. So let's unpack the current situation first. What are we actually trying to replace? Inside the DC, where all the apps live, the standard now is EVPN for the control plane and VXLAN for the data plane, right?
So that's the dominant stack. Yes, EVPN and VXLAN handle everything within the data center fabric itself.
And then when you step outside the DC walls into the big wide world of the WAN,
there you're typically looking at established carrier protocols, maybe SRMPLS, which is becoming more common, or possibly older stuff like RSVP or LDP for label switching.
Got it. So the core challenge is really that translation step. Every time traffic needs to go from an app inside the DC across the WAN to a user.
You hit that wall, you have to somehow reconcile the EVPN VXLAN world with the, let's say, SRMPLS world. Different encapsulations, different logic.
Okay, but before we, declare the old way dead, let's talk about why these setups even became so dominant. There must be good reasons, right? What are the benefits?
Oh, absolutely. There are solid reasons. Starting in the DC, that EVPN VXLAN stack, it's incredibly mature now.
Supported everywhere.
Pretty much universally supported by vendors. And it's versatile. It lets you offer different kinds of services easily. Layer 2 connectivity, complex L3 VPNs, you name it.
And on the WAN side, SRMPLS.
Also very mature, great in multi-vendor environments, and critically, it gives you traffic engineering. Real granular traffic engineering.
Which lets you steer traffic precisely.
Exactly where you need it to go.
Yeah.
Essential for optimizing a large network.
Okay, so the WAN has great TE with MPLS. The DC has versatility with VXLAN. So where's the friction? Where does it break down?
This is where we hit the disadvantages. And this is where let's say, the costs of this separated approach really starts to add up.
Okay.
Let's focus on VXLAN in the DC first. Major technical flaw number one. VXLAN offers basically zero inherent traffic engineering capability. None.
Hold on. You're saying in a massive modern data center, you can't steer traffic effectively with the standard protocol?
Not natively, no.
Wow. Why is that such a big deal?
It's a huge operational bottleneck. If you can't do TE, you have much less control over how traffic flows through your DC fabric.
So you just hope for the best.
You end up relying on, expensive over-provisioning, just throwing bandwidth at it, or basic eCMP hashing.
Equal cost multipath.
Right, which is essentially just praying the traffic distributes itself evenly. If you need a specific path to avoid a hotspot or hit a particular service appliance, VXLAN forces you into really complex workarounds.
Okay, that's limitation one. No TE. What else?
The second major issue is actually at the network layer, the underlay inside the DC. VXLAN, its underlay typically requires IPv4 loopback addresses for the tunnel endpoints.
Still, even now.
Yeah, even though we're well into the IPv6 era, many large DC deployments are kind of stuck maintaining an IPv4 addressing scheme just for the underlay routing.
So no pure IPv6 underlay with VXLAN.
Not in the common implementations for the underlay, no. Which adds complexity, address management headaches. It's just friction.
Okay, so no TE in the DC fabric, and this kind of forced IPv4 dependency for the underlay. This sounds like it sets us up for the biggest headache, actually connecting these two different worlds.
Exactly. Which brings us to what the sources call stitching.
Stitching. Sounds.manual.
It's the operational term for what's really a technical and frankly a financial burden. To link that VXLAN DC domain to the SRMPLS WAN domain, you need a special box.
A gateway.
Often called the DCI Gateway Data Center Interconnect. And this device, it has to be smart enough or complex enough to handle two totally different encapsulation methods at the same time.
Okay, so one side speaks VXLAN, the other speaks MPLS, and this box translates.
Precisely. It has to strip off the VXLAN header coming from the DC, look inside, figure out where it needs to go in the WAN, and then wrap it all up again with an MPLS label stack.
That sounds like a potential bottleneck.
It absolutely is. It's a mandatory translation point. So yeah, potential bottleneck, an extra point of failure, and often it leads to vendor lock-in because you need pretty specialized hardware and software to do this dual stack translation at line rate.
Right, not just any router can do that heavy lifting.
No. It's an ongoing operational expenditure nightmare, really, managing firmware, capacity, policies on these critical boxes.
And I imagine this gets even more complicated when you want to do more than just basic connectivity, like service chaining, putting a firewall in the path.
Oh, yeah. That's where the complexity really explodes under VXLAN.
How so?
VXLAN can technically handle service chaining, redirecting traffic through, say, a firewall or a load balancer, but the configuration is just cumbersome.
Cumbersome how?
You're usually forced into using complex policy-based routing, PBR.
Okay.
Or maybe you have to configure the service appliance as the default gateway for certain subnets, which gets messy. Or sometimes you see these awkward VLAN handoffs.
Can you unpack the PBR and VLAN handoff issues?
Yeah.
Why is PBR such a pain?
Because PBR isn't simple routing. Every time you want to insert or change a service, you're not just tweaking your route, you're writing potentially complex policy maps, maybe hundreds of lines of rules that classify traffic and dictate specific next hops.
Which sounds brittle.
Very. It needs constant care, feeding, auditing. And the VLAN handoff approach, you're essentially carving out a layer 2 segment just for the service device, which wastes IP addresses and kind of breaks the whole idea of a clean routed fabric.
Okay, so let's recap the problems. We've got the multi-protocol dependency, the IPv4 underlay issue in the DC, the big one, no native traffic engineering in the DC, and then this complex, expensive stitching needed at the border, which also makes service chaining hard.
That's a pretty good summary of the pain points, yes.
And this is where SRv6 comes in, claiming to solve all of this.
That's the claim. SRv6 is positioned as this fundamental architectural shift.
How does it achieve that? How does it unify things?
Well, the fascinating thing is SRv6 doesn't try to translate or stitch the old protocols. It aims to make them, well, unnecessary in many ways.
How?
By creating a truly unified data plane that's purely based on IPv6 from end to end.
End to end meaning DC and WAN.
Exactly. DC, WAN, Edge, Core, everything speaks IPv6 natively. And because the whole network is now using a single routing language,
You don't need the translator box, the DCI gateway.
precisely, you completely eliminate the need for that specialized, complex stitching point because there's no translation needed. It's just IPv6 routing all the way.
Okay, that sounds almost too simple. Isn't the complexity just moving somewhere else? Like into the packet header itself. SRv6 headers carry segment lists, right? That sounds complex too.
That's a fair question. And yes, complexity does shift, but it shifts into a structure that's actually far more standardized and inherently programmable.
Which is?
The segment identifier list, the SID list, carried in an IPv6 extension header. The core idea of segment routing is that the source encodes the entire path or the required functions directly into the packet.
So the packet carries its own instructions.
Sort of, yeah. It carries its own roadmap. Every SR-capable router just needs to look at the current active segment in the list to know exactly where to send the packet next or what function to perform.
Okay, I see. The intelligence is in the edge and in the packet, not necessarily complex state and middle.
That's a good way to put it.
So that unification is powerful. It solves the stitching problem. But you mentioned SRv6 also addresses those functional gaps VXLAN had, like the traffic engineering.
It does. That's a major win. Remember how we said VXLAN had no inherent TE?
Yeah, the big limitation.
SRv6 provides full traffic engineering capability natively, both in the WAN and now, importantly, inside the data center as well, using SRv6 traffic engineering or FRv6-TE.
How did that work?
Because the source node, maybe the first router the packet hits, defines the sequence of SIDs, the segments the packet must travel through, so you get that granular end-to-end path control.
Yeah.
Even within the DC fabric itself, you can steer traffic precisely.
Okay, that directly tackles the big VXLAN weakness. What about the other complexity we discussed, service chaining, those PBR nightmares?
SRv6 simplifies that dramatically too.
By using SIDs again.
Exactly, because the network functions themselves, the firewall, the DPI engine, the load balancer, they can each be assigned their own unique SRv6 SID.
Ah, so they become just another stop on the path.
Precisely. The service chaining function becomes, well, almost implicit. It's just part of the path definition. It's by default enabled, you could say.
Okay, walk us through that firewall and DPI example again, but with SRv6.
Sure. So in the old VXL MPBR world, you needed complex rules to spot the traffic and force it over to the firewall.
Right.
In SRv6, it's just routing. When a packet enters the network, the source node calculates the needed path. Let's say it needs to hit firewall A, then DPI B, before getting to application C.
Yep.
The source simply puts the SIDs for those functions into the SRv6 header. The list might look like SID for A, SID for B, SID for C.
So the packet arrives at the firewall.
The firewall sees its own SID, SIDA, is the active segment. It performs its firewalling function. Then, because it's an SR-aware device, it looks at the next SID in the list, which is SIDB.
The DPI engine.
Right. And it simply forwards the packet towards the location associated with SIDB using standard IPv6 routing towards B's locator. No PBR needed.
And the DPI does the same. Performs its function, looks at the next SIDC, and forwards it on.
Exactly. The service device just executes its function based on its segment being active, then forwards based on the next segment. It's a massive simplification. You replace complex, stateful policies with simple, explicit path definition in the packet header.
That inherent efficiency seems like a game changer. Okay, to really hammer this home, let's use that practical example. Setting up a standard L3 service, like an L3 VPN, that needs to run from a host in the DC all the way out across the WAN.
Yeah, this is where the elegance really becomes clear. In the multi-protocol world, doing that cross-domain L3 VPN was complex.
How so?
That DCI gateway had to manage MPLS label distribution for the WAN side, EVPN VXLAN mapping for the DC side, maybe BGP L3 VPN signaling. Lots of interacting parts just to extend one VPN.
Right. Okay, so with SRv6, how much simpler does that L3 VPN setup become? You said minimal configuration earlier.
It becomes remarkably minimal. Essentially, only two types of devices really need to have the SRv6 service capability fully enabled. The provider edge, or PE router, out in the WAN where the remote user connects, and the leaf switch in the DC fabric where the application server is connected.
That's it, just the endpoints of the service.
It's the service intelligence, yes.
So, wait, what about all the routers in between? The core routers, the aggregation routers, the DC spine switches, they're carrying the traffic.
And here's the crucial efficiency gain. Those transit devices, they generally don't need to be SRv6 service aware.
Really?
They just need to be baseline IPv6 capable. They just need to know how to forward an IPv6 packet based purely on its destination IPv6 address. That's it.
They don't need to understand the service SIDs or the VPN context.
Nope. The complexity, the service awareness, is pushed entirely to the edges, the PE and the leaf in this case.
And if the middle routers only look at the destination IPv6 address, how does the packet keep the context? How does it know it's part of L3 VPN Blue or needs to hit that firewall SID we talked about?
That's the clever part. It's baked into the structure of the SRv6-Segment ID, the SID itself, which is the destination address the transit routers look at.
Okay, how is it structured?
An SRv6 SID typically has two main parts. There's the locator and the function.
Locator and function. Break that down. What's the locator?
The locator is the most significant part of the SID address. And fundamentally, it's just a standard routable IPv6 prefix that points directly to the specific edge device providing the service.
So it routes you to the right PE or the right leaf switch.
Exactly. The transit routers only need to look at this locator part to forward the packet correctly across the network using standard IPv6 routing tables.
Okay, and the function part?
The function part is usually the less significant bits of the SID address. It tells the receiving edge device, the one identified by the locator, what specific action or service to perform when the packet arrives.
So in our L3 VPN example,
the function might specify, okay, this packet belongs to VRF Blue, so the leaf switch gets the packet, sees the destination SID points to itself, its locator, and the function bits tell it to do the L3 lookup in the VRF Blue table.
Incredible. So the transit network just does basic IPv6 routing to the locator, and the edge node uses the function bits within that same address to apply the right service.
Precisely. Lookup based on locator plus function provides the service context.
Wow. Okay, so summing this up, we've shifted from this world needing two protocols, complex stitching boxes translating VXLAN and MPLS,
Right.
to a world where one protocol, SRv6, runs end-to-end. The middle of the network just needs basic IPv6 forwarding, and all the service smarts, like VPNs or service chains, are handled at the edges, encoded into the SRv6 SID structure.
That's the core idea. The benefit is really architectural sanity. You're tackling those major pain points we listed. No DC traffic engineering, the awkward IPv4 dependency, the unclocked stitching, all by unifying everything under IPv6 routing.
It really feels less like an upgrade and more like, as you said, eliminating that artificial distinction between the DC and the WAN.
Exactly. It becomes just the network.
This has been a fascinating deep dive. Really clarifies how SRv6 aims to simplify things. For anyone managing large networks, the potential operational savings, moving from that multi-protocol tangle to a unified SRv6 plane, they seem pretty compelling.
They are, and that actually leads me to a final, maybe provocative thought for our listeners to chew on.
Okay, let's hear it.
Think about the traditional network engineer. A lot of specialized expertise was needed just to bridge those complex domain boundaries, right? Understanding MPLS label stacks, VXLAN tunnel endpoints, EVPN, BGP extensions, how to make them interoperate.
Sure, deep specialization in multiple complex areas.
Right. Now, if SRv6 fulfills its promise, and basic transit devices only need to understand simple IPv6 routing based on the destination address, the locator, and all the complex services are defined by that function part of the SID, handled at the edges, perhaps increasingly programmatically. What does that fundamental shift towards service-aware, destination-based routing mean for the kind of expertise we'll need in the future? What skills become more or less valuable when the network itself understands services natively via the address? Does the focus shift entirely to the edge, to automation, to service definition?
That's a really interesting question about the future of network engineering roles themselves. Something definitely to think about.
Indeed.
We'll leave you with that thought. Thanks for joining us on the Deep Dive.
My pleasure.
We'll see you next time.